Good morning or good afternoon or good day, whatever this is. Welcome to Lecture 3, which is occurring during fall break at Oklahoma Christian University. I am recording this ahead of time so that you can watch this and then hopefully you're able to work through the lab and homework assignment based on the material here and in the text. We're going to be looking this week at a library called MPI. It is the Message Passing Interface. What we're doing here is simply an introduction, and we're going to cover mostly things that are in the text, might mention one or two other things. And so for augmenting everything that I say here, I strongly encourage you to go to the text and look at the, I'm going to turn this fan off in case it's creating noise, background noise. And so I encourage you to go to the text. It will provide additional information on MPI as well. And so what we're going to do is we're going to run through MPI, some of the functions, some of how it's used. Then I've got an example program that I wrote where I took a commonly used algorithm, a Monte Carlo simulation to try to determine the value of pi. And I've turned it into a parallel program using MPI. And we'll walk through that so you can kind of get one big picture of how all these different features and functions that we're going to talk about work. All right, so MPI is a standardized portable message passing system. This is MPI Message Passing Interface. And I personally kind of think, okay, I understand why it's called Message Passing Interface. We're typically going to use this in systems that are distributed memory. And if you recall from previously, a distributed memory architecture, each processor has its own memory. And so if processor A has some value that it's storing or managing, processor B needs that value, they have to send messages back and forth to each other in order to get that value communicated from one processor's memory into the other processor's memory. But if you just call this message passing interface, you really miss the heart of it. The heart of it is that there is an underlying supporting architecture with a lot of data structures and a lot of work that allow us to run a single program, multiple data architecture parallel program. And so this interface here is going to allow us to parallelize code that otherwise would be run in serial. It works with C++. It works with Fortran if you've got to work with Fortran. I don't know anyone who works with Fortran anymore. It was a very popular language in the 70s, 80s, and 90s, but it has declined some. Some people still use it. It is a very efficient language. It gives us a lot of support for some things that we might have to do by hand. Yay, every time someone's going to write something, a library that's going to do stuff for me, I'm very, very happy with it. Again, we're going to associate it with distributed memory architecture. And go back and look at your notes and what distributed memory architecture is. And when you do, you'll see that there is a requirement for a lot of communication between the different processors. And so this is the tool that will allow us to take a single program, have that program figure out what its process number is, and then run appropriate code for that process number. Here's a picture, and basically when we start and end MPI, this would be a typical MPI code. This is written in C, and there are two commands that we're interested in. And be aware that when your program first starts running, it is not automatically in parallel. You may have multiple programs, each running their own upfront serial version on different processors. And that would be, let's see if I can get a laser up here. Hang on just a second, see if I can make that work. Oh, where's the laser pointer at? There it is. There it is. So you would have some serial code. In this case, there's nothing, but it would happen before MPI init. And then we call MPI init, which initializes our MPI environment. Now, a lot of times people take argc and argv, which are the classic argument count and argument vector, which would be the things that were on the command line in the Unix shell or in a DOS shell, and then they pass that to MPI init. In our programs for this class, we're not going to worry about this. So what we'll actually pass, as you'll see later, is null, comma, null. We're basically going to say, hey, I don't have anything to give you, but I want you to set up all the data structures. I want you to set up all the communication between all the other processes that are running on all the other processors. Then we would put our parallel program code here in the middle. And when we're done, we just say MPI finalize, which is basically just, hey, clean up. And then, of course, we would return 0. And so This is the kind of beginning and ending, and we'll put all of the other code in the middle. Let's see, I think I have to turn this off in order to switch slides. There we go. So how would you build this on OU supercomputer? I'm going to take a quick side thing here. This is somewhat documented in Lab 1, so I want you to go back to Lab 1 and take a look at that. However, I thought I would include it here since you're going to write an MPI program for Lab 3. And so what you do is you would write your C program and you would include your MPI commands. And there's again, Lab 1 is there so that you can go back and look at that. It describes a lot of that. Before you compile your C file, you're going to write a C file. And if you write it locally on your laptop and then copy it using FileZilla, fine. Be aware you may have to do that DOS to Unix to modify the carriage return line feed, which is a DOS environment, but the Unix doesn't like that. The Unix, if I remember right, only wants maybe carriage returns. So when you're ready to compile your code, first you're going to have to load a module into your shell environment on Unix, and you use this command, module load, open MPI. Then you can compile it with the MPI CC command. Now, for those of you that are a little more adept in Unix and have done some G++ or C++, this is actually a wrapper command, and it's going to call the appropriate C compiler, but it's going to add all the flags that we need for MPI. So just use the MPI CC command. This mycfile.c, this would be your MPI file that contains C code and MPI calls. And this -o says I actually think of it as the object file, but it would be your output file, and this is usually the executable code right here. So this is the command you would use to compile it and create an executable code. And then you guys should have already used something with the SBatch file back in Lab 1. And again, here we can say we can ask for up to 2 nodes. Don't ask for more than that, you won't get them. Your program will never run. I've tried. And then you can say how many tasks you want or how many processes you want. And you can say up to 40, and you can have up to 20 tasks per node. And so that's why you can only have up to 40 processes, and that's plenty for us. So this is in the SBatch setup. This is basically setting up the environment where your code will run. Then a little below that, you want to run your code. Now remember this SBatch file is being transmitted to the supercomputer from the front end. And so on the supercomputer, you have to tell it, there's another thing in here which I didn't include. You have to tell it what directory to go find, and it will find that directory. And once again, you'll load the Open MPI library, and then you can use the MPI run command to run your executable. And this executable right here is the name from the compile command up above. So all of this down here goes in the SBatch file. That's what you submit to the computer. All of this is the process of interactively compiling the code. Here's a copy of the SBatch file. No, I've left a lot of stuff generic here, but just kind of walk you through it, make sure you see a couple. Here's that nodes equal 2. Here's ntasks equal 40, and then tasks per node. This is the output is job name %J standard out. This is your job number. You will recognize that from the other files you've already seen from previous runs. This is where your standard out file goes. So you could change this if you wanted to change the standard out file name. And job name, blah, 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 standard error. This is your standard error output. This is a max time. I would be shocked if you run more than 10 milliseconds, so 10 minutes would be insane. You can give it a job name. Here, this email address is your OC email address. You're just telling it it's going to use all types of mail. And then this is the directory where your code is. So if we go back to the previous slide where we know what folder, I say folder because that's a Windows term. On Unix, it's a directory. And so this is the directory where your code is, and here's the load. Now, one little tip I'll give you that I used quite a bit when I was learning this last summer and have played with it over the course of the fall is this is a batch file that's going to run shell commands. And you are able to put shell commands in here. For instance, you can do an echo command here that says echo, I'm about to run my program, and you can have one afterwards that says echo, I'm finished running my program now. And that can help you locate stuff in the output. Some of the output files can be filled with a lot of extra material that you don't care about, and putting some echo commands in there can help you debug or can just make it a little easier to read the code. So those 3 files, the previous 3 slides give you that idea of exactly what you need to do to try to get your MPI program up and running on the OU supercomputer. All right, so we're back to MPI. When we initialize it with the MPI init, the things that happen in the background are we set up all the processes. The MPI will assign a rank value to each process. We can find out what it is. I'll show you that in just a minute. And it sets up all the communication data structures that are there to support messaging between the processes. We're not going to use any arguments, as I mentioned before. We're going to put, let me get my laser pointer up here again. We're going to put capital N-U-L-L, capital null, all caps null here. And that will basically say, look, I don't have any special instructions to give you from the exterior command line. And so this is, you'll see this. I'm going to give you an example in a little bit, but this is the starting of it. You put a bunch of code in between, and then at the end you do that. All right, so let's talk about the MPI elements or data structures or support structures. First of all, there's something called a communicator. And the communicator is, in my opinion, a data structure that hides behind the scenes. Every one of your processes has a copy of this communicator. It lists all the other processes. It's going to list all the addresses, how to send data back and forth from one process to another. It's all hidden, thankfully, because we don't want to have to manage all that. So the communicator is predefined for us as well. Once we initialize MPI, we can start using this variable name. It's a constant, MPI com world, and that will refer to the communicator. And so this first command here, MPI com rank, is used to get my current process ID or my processor's rank. Am I process 0, 5, 100? What's my process number? Notice that up here we define an integer called myRank, and down here we pass the address of that integer. We're giving it to the function by reference so that the comRank function can write the number into it and basically return it to us. So notice this doesn't have a return value per se, but because we pass this variable by reference, we're able to find out what our process rank is. And we're going to use that in our SPMD code that's going to come below this. Similarly, we often want to know how big, how many processes there are, and so this function does exactly the same thing. We have an integer for the number of total processes that are running in parallel, and this returns that value to us so that we can use it. And now what's going to happen for the rest of the code is we're going to have those if statements. If my rank is 0, do these things. If my rank is not 0, do these other things. All right, now how do we send messages and data back and forth? The basic structure is a function called MPI send. And again, I apologize because my slide deck that I'm using does not allow me to use lowercase letters. This is a cut and paste from my Visual Studio. And so here you can actually see the correct syntax for MPI send. The MPI send function is used to send data from the process that is running the function to a specific other process. And it's very simple. It's basically going to take the data that you have, copy it into a buffer, send it over to the receiving process, and when that receiving process posts a read, if you will, it will then read the data and be able to do something with it. So this is the sending side. And it has 1, 2, 3, 4, 5, 6 parameters. The first one is the address of the data we're going to send. And this could be an array, for instance, an array of integers. And so that's why in the second parameter, we have to tell it how many elements we're going to send. In this case, this function is going to send one integer variable. Now this MPI int stands for MPI integer. There are other ones that you can look up in the text, MPI double, MPI char, MPI whatever. So we can send different types of data here. And then this one is this 1, 2, 3, fourth one, this is the destination process. And by convention, we're going to let process 0 kind of be the master process. And so we're going to send our data to process 0 here. And then finally, this 0 is a tag. Now, it might be that you're sending 2 bits of data to process 0, and they're both integers. Now, how's process 0 going to know which one goes to the sum and which one goes to the clock or something like that? Well, you can put a tag in there, and this tag is an integer that delineates between one message and another. So this tag could be 0 or 1 or 12. we would probably typically define some constants and use constants here to make our code more readable. But in this case, we are not going to send more than one kind of message. So we are simply going to record it. Say, hey, I'm going to send this to process 0. That's this guy. The tag is 0. That's basically just a default. And I'm going to use the communicator that already exists for me. And so this is the send side. Now, here's the receive side. It looks very similar to the send side, except there's a little bit more data here that the receiver can worry about. First of all, the receiver has to provide the address of a local add variable where the data that was received can be sent. He also has to say how many bits of data, how many integers or whatever he expects to receive. And again, this could be used to send an array, for example. And again, he specifies the type. He says, I'm going to receive an integer. And the source address, he has to say, look, I expect to receive something from process 12. Now we'll see a little later that there is a predefined value that says, hey, I don't care, I want to receive from anybody. So it's possible for you to kind of have a wildcard here. We'll look at that a little later. And then here's that tag number again. Notice that we match the tag and 0. We're just using 0 because we don't have any specific delineation between types of data. Here's our communicator, MPI COM world, all those data structures in the background. And then finally, here is the status ignore. Now, this is going to come with a status. A lot of times you want to know, well, you want to know bits of data or bits of information about the send. And so there is actually a status data structure. I encourage you to look in the book to read a little bit more about that. We will not use that in our programs in this course. But if you were wanting to know important bits of status about the data that was sent to you, you can actually provide a status data structure here. It will fill the data structure in, and then you can query that data structure all you want. But we're just going to say here, hey, I'm just going to ignore that data structure, all right? Okay, so let's go on. Now, how are the receive and the send messages matched up? Basically, messages are matched if the receive communicator equals the send communicator. That's that MPI COM world. So they have to be using the same communicator, which is the data structure underneath. If the tags match, then they might. Then we're moving along. If the receiving process rank equals the sending rank specified by the sender, in other words, if I'm sending to process 5, then only process 5 can receive it. And similarly, if I'm the receiver and I say I want to only receive from process 12, then the sending process better be 12, all right? And then the types have to match. So I have to send integer types or double types or whatever. So if all these things work out properly, then, and only then, is the message going to be received by the receiver who posts an MPI receive message. Notice that, here's that thing I mentioned earlier. MPI any source. If you're willing to receive from any sender, you're just willing to get spammed by everybody out there, then you can say, look, instead of specifying a specific number, you can use this constant MPI any source, and that will allow you to receive from anybody. So we'll overcome element number 3, the third one here. Now, just a few more details about how this works behind the scene. It depends on the implementation as to how it's going to actually be transmitted. And you can go query. I have not done it for OU Supercomputer, and I don't really care that much for the purposes of this educational experience. So you can, but there's two ways that MPI might handle it. It might send via a buffer, and if it does that, then it's going to copy the data from the sender's location to a private memory location, and then it's going to wait for the receiver to say, hey, I'm ready to receive, and it will, transmit it over. But it will not block the sender. The sender will be able to go on, and as soon as the return from the MPI send comes back to the CPU control, then at that point, it's safe for you to modify that data, because by then MPI background stuff will have made a copy of the data. So let me say that slightly differently. You've put a value in variable X. You send variable X using MPI send. When the call returns control back to the sending process, then X has either been sent or copied to a buffer, and you can change variable X. You will not affect the message. All right. It's also possible that MPI will block. In other words, it will stop executing the process that sends until it gets confirmation of the receipt. In either case, once you return from the send call, you may modify the data without worrying about damaging the data that was sent. Now, on the receive side, if you post a read, I call it posting a read. If you post a receive, it always blocks. You're going to wait until a matching message is sent to you. And so this does require you to do some careful programming and make sure that you have all those things matched up that I showed you in a previous slide, and that if you say you're going to receive from process 4, at some point process 4 better send you something, or that particular subprocess is just going to hang. And it's really important that you think carefully through that. Now, when you post your read or your receive, assuming there's nothing wrong with it, the storage location you specify will have the data that was sent to you. And again, there are two kinds of, let me back up. In bold down here at the bottom, let me get that laser pointer. In bold right down here, there are several kinds of send and receive options. We'll see more references to these in week 6 when we do an example at that time using the traveling salesperson problem. And so I think if I remember right, there are 4 different kinds of send and receive options that block or don't block, and send with a buffer. We can force some of this to take place by specifying the kind of send and receive we're going to do. And so there is a way for us to control this a little more deeply. At this point, we're just going to use the standard receive and the standard send. All right. Now, we talked in our first week, that would have been 2 weeks ago, about this idea of each process did some work, and then they all had to send it to the main process, and the main process did all that addition. And we talked about how to make that more efficient. Now, one of the nice things about MPI is it will do that for you. You can call an MPI reduce function, and a reduce function says, take all of the data that every process has and combine it and do something useful with it and reduce it to the bit of data that you want. So for instance, you might have a bunch of, you're going to see this in the example a little later, you might have a bunch of values and you want to know the largest of those. Every process calls MPI reduce, they each submit their value, MPI reduce does the work of finding the max, and then you can it gets delivered to a process that you select, usually process 0. So the reduction has these different functions. It could be that we want to add all the values, or we want to multiply all the values, or find the minimum, or find the maximum, or things like that. So this MPI reduce function gives us the ability to do that. This is called collective communication because all the processes collectively share in that one communication. They all put the data in, MPI does the work and delivers it to the right place. The receive and send we just looked at are point to point. There's a specific receiver and a specific sender. You can kind of think of this as multi-point to point, this MPI reduce. All right, so here is an example of MPI reduce. You'll see this in the example I'm going to give you in a little while. Here's the call. In this particular call, we are trying to find the longest time from the wall clock performance of every process. So previous to this code that you see in black up here, let me get my laser pointer. In black up here, previous to this, every process has determined what its total local elapsed time was. And so it says, I'm going to reduce that. And I'm going to reduce that down to the one that was the longest wall clock time. And that's going to be the wall clock time we use to measure our performance. Remember last week in week 2, we looked at performance variables. And here we're actually using MPI reduce to find that longest wall clock time among all the processes. So first of all, we pass our local variable, which is the number or value or variable that's going to get reduced. And then we pass the address of a local variable where the answer is going to go. In this case, we're going to do a max. So the largest of all the values submitted will end up being stored in elapsed. All right. And third, how many data elements are there? Well, we're only sending one in. We're not doing an array or anything like that. So that is 1. We tell it what type it is. This is a double. And we tell it which function we want. We want the max function. And then finally, after the max function, we say which process is going to receive the final result. In this case, we use the kind of the default process 0, and again, we must provide the communicator data structure that helps all these things talk together. This is really efficient. It will work behind the scenes. It will do it, will not add a lot of extra time to your code. It will do it effectively and efficiently. So this is a great little function. And it's nice that we don't have to write that code anymore. We can just use that. And speaking of timings, let's look at how we would take timings from a parallel performance. Now, when we do parallel performance timings, one of the big questions is, should you measure wall clock? Should you measure CPU time? If you think about it, CPU time is kind of pointless, because if you distribute the work among 20 processors and then you add all that work back up again, well, it's going to equal the amount of work plus some overhead. So it doesn't really tell you much. What we really want is we want to know, look, I had a program that took 1 hour to run. I want to know how much I've improved it. So I'm going to look at the wall clock time. It doesn't take an hour anymore. If it goes down to 10 minutes, then I'm running in 16% of the time. So that's what this guy did. I'm using two functions here. Let me get my pointer. One of the functions is called wall clock time, and it gives me the current wall clock time in the system. And I'm going to store that in a double start time. All right. And then down here, when I'm done all my code at the very end, I'm going to get the wall clock time again and store it in the finish time. And then I'm going to say the elapsed time of this process was finish time minus start time. Now, there was something I just realized I forgot. What is this barrier thing here? This is a synchronization point. And I'm going to do this before I start measuring time. This is like a starting line in a NASCAR or a high performance car race. All of the processes are going to come to this barrier, and they're basically going to wait for a green light. And the green light won't come until all of the processes are there and ready to run. And so this will ensure that all of the processes start at roughly the same moment. We don't want to have some come in earlier than others. We prefer to have a synchronized start. And so the barrier, MPI barrier, causes all of the processes that are sharing in this communicator to start at the same moment. We get all their start times, and then we get their finish time at the end. And then it's right after this that we could use that reduce thing to get the biggest and largest value. All right, so we've gone through the various different examples of some of the commands that we're going to use, that you're going to use. Now I'm going to show you the code that I wrote to modify a Monte Carlo simulation. I got the Monte Carlo simulation from some source. I didn't write the Monte Carlo simulation myself. What I was interested in doing was seeing if I could parallelize it. And I've been able to successfully do that. And I'm going to show you the code. And it used MPI, so I think it's a really nice, tight, and simple illustration of that. And so what we're doing is we are going to try to generate random points in a 1x1 square. And you can see this blue line, that's the edge of a circle. Points that fall inside the circle will be measured in ratio to the points that fall outside the circle. And that ratio should be roughly equal to pi. And I'll let you go look that up to figure out how. But just know that we're going to basically be generating random points, as many as we can. We're not going to generate 1 million. We'll do 10 million or 100 million. That's going to also, this is a nice simulation for parallel programming, because using this, we can run as many points as we want. So in essence, we've got a really cool program. We can run it as many iterations as we want, and that makes it easy for us to do some checking with the clock. All right, so here we go. First of all, we've got our include file. You have to include mpi.h. And then here is me declaring all of the variables. And you can stop the recording and look at these if you want to. As you can see, I'm going to do 1, 2, 3, 4, 5, 6. I'm going to do 10 to the 9th points. And I'm doing a large number like that so that I can actually get some value out of parallelizing this thing. If I only do 100 points, not only do I get a terrible value for pi, but I'm not really going to get any parallelization out of this thing. The larger the data set, the better off we are. Then I've got a double here for pi estimate, -2. I didn't put a comment here. And then I've got a value to count the number of points inside the circle. I've got a variable that's going to tell me how many points of the iteration this process is going to do. This isn't points in the circle. This is points in the iteration. And This is going to, and then I start the MPI init. I really meant for this to be down lower. It got copied up here when I was messing with the code earlier today. So please, in your mind, put that down low below these other variable declarations. Then I've got a start time, I'm sorry, a start location for the number of subsets to generate. This is going to be the start and end of my loop. And then I've got some doubles to calculate wall clock times. I've got an integer for my rank and an integer for my number of processes. These are just the variables that I need in this little Pi program. Now here I am starting MPI and starting the wall clock. So first of all, I get what my rank is. Let me get the pointer up here. Man, I get what my rank is. If I'm 0, I'm going to do a certain set of work, and if I'm every other process, I'm going to do a different set of work. I also get the number of processes, and it's particularly process 0 that needs to know this, because it's going to expect to receive a message from every other process, so they can get a total of the number of points generated within the circle. Once this is done, we set that barrier up to synchronize all the processes so that they will operate at exactly the same time. And we start the wall clock timer. So that's what these two last things do. Now we're actually ready to do the work. And so first of all, I've got to do a little bit of work to figure out, I'm process 5, and I'm doing all the processes together are going to do 100 million points. Which points am I going to do? Am I going to do points 0 to 100,000, 0 to 9 million? Which points am I going to do? So this little bit of work figures out what points, what's my starting iteration and my ending iteration of the larger for loop that would go from 1 to 100 million. Maybe I'm going to do 1.25 million to 2.5 million. Those are going to be my dots. And so I generate the start and the end. You should recognize this from homework 1 when you did something very similar. I'm being lazy. I make sure that the number of processes is a multiple of the number of the number of iterations is a multiple of the number of processors. So I don't have any left over here that I have to worry about that might mess with my Monte Carlo simulator. Then down in here, I've got for int I equals start, and you notice there's nothing here. Every process is going to run this. Every process is going to calculate for its start and its end the number of random doubles. It generates a random x and a random y. And then this is how you determine if it's inside the circle. If x squared plus y squared is less than 1, then that is inside our circle in a unit square. All right? So this is just the Monte Carlo simulator. There's no parallelization really going on here, except to be aware that well, there is right here. Let me get this pointer up here. This is the parallelization right here. Because what this is doing is it's each of the programs that are running on the different processors have a different start and end, and so they each run a different set of points to simulate. Okay, now we've figured out how many points are inside that circle, and what we're going to do is we're going to say, hey, am I process 0 or above 0? And this is the code that's going to run if I'm not process 0. And if I'm not process 0, I'm going to simply send my points that I found using one integer. Now let me get this laser pointer. My points that I counted using one integer to process 0, tag 0, I'm going to use my world communicator. Now, those of you may be thinking, why didn't you use MPI reduce? I could have. I could have used it, but I wanted to give an example of MPI send in here, so I used MPI send. I actually think this would be more effective to use MPI reduce, because I ended up doing kind of an inefficient send here in the way that I did it. Now, here is the process 0, and you can see that process 0 is a lot more complicated. Let's kind of walk through this. First of all, process 0 has calculated its own points in the circle, and we're going to sum them all up. So we start by assigning that to our total points. Now, this local point variable is going to be used to store the number I receive using the MPI receive. And now I'm going to run a loop down here that runs from process 1 all the way through the number of processes, and I will receive the local point count from each of these guys. So this would be receive the local point count, which will copy it into there. From I'll have one integer, and the source is my loop variable, so it'll go from 1 to whatever. And then here's the tag, here's the com world, and I'm going to ignore the status. Then after I receive the local number of points from process 1, I'll add that into my total points, come back up here and receive the points from process 2. What happens if process 3 sends before process 2? Well, that data will sit here and wait, but I'm not going to receive process 2 until after I receive process 3 because I've written a little loop here that sequentially receives all the data. You might, I don't know, I think it'd be a little more work, but you might say, hey, I'm going to use that MPI any source and say, I don't care who sent it to me, I'm going to add it in because they're all each going to send me one. And then you would just do 7 of them and add them in and you're good to go. All right, so then we've here in this loop, process 0 has received all of the data from the other processes. And now he's the only one that's going to actually print this out. Hello from process, it'll print a 0 there. It'll say process number 0, total points, and it will print out the total points from all of them. And then this is the math here for the Monte Carlo simulation. I have to multiply it times 4 because I only did 1/4 of a circle. So I do 4 times the total points over the number of points. And these are integers, so I have to do a static cast. And that gives me the value of pi, which only process 0 prints out. Notice, else we are in process 0. All of this code in this window is the code that process 0 ran. Processes 1 and above do not run this code. Processes 1 and above run the code on the previous slide. All right. So that's it. That's pretty much the heart of it. Now we're going to get some timing stuff out of this and close up shop. So I'm now going to run the wall time again, and I'm going to set that equal to my finish time. I'll calculate my local elapsed time. That's on the next line right here. And then I'm going to use MPI reduce to get the max time. And if my rank equals 0, notice this is running outside of that if. So all of the processes are going to run this code. They're all going to run MPI reduce, but only process 0 is going to put the data out on the screen. That's going to be our convention. Process 0 will have access to the standard in and the standard out, and the other ones will work through process 0. And then we clean up with MPI finalize, and we are done. So there's an example. You can go back, through the presentation and look at each of the elements, but this gives you kind of an idea of how MPI can be used to write a single program, multiple data parallel program. And so this is the end. This is the summary. MPI provided us a library. We managed communication. We managed our processes, did reduction for us, allowed us to take timing. And you noted in my example that we write single program, multiple data programs. So one program, the same program, is run on all of the processors, and we use if statements to control which code is run where. So, the process 0 says, I'm process 0, I'm going to run this section. Everybody else runs a slightly different section. Typically, MPI is used on a process level, not a thread level. When we look at OpenMP, we'll look at thread level parallelization. And it usually runs on a distributed memory environment because it's all about sending messages and managing communication. Now, you have the job of implementing an MPI program for the lab. It's a version of a program that's in the text, so I think it's going to be a kind of a good introductory one for you. You'll be able to go right to the text, use some of the code there, and get your MPI communication stuff up and running. I wish you the best of luck. Feel free to email me. I am not sure what I'll be doing over fall break. I may be out in the yard for hours and hours, but when I see your email, I will.